Good morning, students. Before we begin our question on alkenes, let's study a little bit of theory related to them. What we are going to understand is how alkenes are prepared. The first method is called the controlled hydrogenation of alkynes, and there are two particular pathways for that. So tell us more about them, Gopi.
Consider the first pathway where you use reagent palladium in presence of barium sulfate. Here you will get a cis alkene, whereas if you use second reagent, that's sodium and liquid ammonia, which is also known as a Bitz reagent, this reaction is called as Bitz reduction, and you will get a trans alkene. Now let's study the second reaction, which is
the mechanism we'll deal with later.
Yeah.
Okay, so you just need to remember, if you see sodium in liquid ammonia, it's going to be trans, and if you see BaSO4 in quinoline, it's going to be cis.
Yeah.
Alright, let's move on to dehydrogenation of alkyl halides.
Yeah. In the dehydrogenation of alkyl halides, you have two reactions. One is called E2 elimination and one is E1 elimination. Now, for E2 elimination, we use reagents like alcoholic KOH, NaNH2, NaOET and tertiary butoxide ion, and the solvent which we use here is polar aprotic solvent. I'll tell you an example for it.
So what particular compounds or radicals do the reagents provide as such for the reaction?
The thing is, in E2 elimination, we won't get any intermediate.
Okay.
It's a concerted step.
Okay.
And there won't be formation of any ions.
Alright.
So we use polar aprotic solvent because if you use polar protic solvent, they provide H plus ions.
Yes.
They'll stabilize anions. Suppose say Cl minus ion.
Okay.
By electrostatic forces. But during the reaction, we are not getting any ions.
Okay.
As a result of it, we use polar aprotic solvent.
Okay, so it's going to happen simultaneously. Like one atom will attack and the other will leave simultaneously without the formation of a transition state.
Yes.
Okay.
H will leave and Cl will leave. You will get a double bond here. And you can get a double bond this side or on this side.
Okay.
This is the most substituted one and it's called as Saitjev product. It's a less substituted one and it's called a Hoffman product. And in general, Saitjev product is more stable, but Hoffman product is less stable. But there are some exceptions for it, which you will see later on in the examples.
Okay.
Now, let's come to E1 elimination. The name E1 suggests that here E indicates elimination and 1 indicates unimolecular, which means in the RDS, that is rate determining step, only one molecule is taking part.
Which means we'll have an intermediate, right?
Yeah.
Okay. And which is why E2 was bimolecular, because two were leaving at the same time. Alright.
And here the intermediate is carbocation, and as you can see, we use polar protic solvents here. Because for example, you can have polar protic solvent as say water.
Alright, so it's going to have H plus ions.
H plus and OH minus ions.
Okay.
This OH minus ion stabilizes this carbocation.
Carbocation. Alright. So this is dehydration of 2 and 3 degree alcohol. But what about 1 degree alcohol? What happens with them?
Simple primary alcohols undergoes dehydration by E1 elimination.
Okay.
Sorry, E2.
Alright.
But there are some exceptions for it. I'll tell you that later on in the next one.
Alright. So with this we conclude our first section of the theory on alkenes as such. Let's move on to part 2. So continuing with the dehydration of alcohols, we are now going to study how simple 1 degree alcohols or primary alcohols undertake E2 elimination, right?
Yeah.
Okay.
First one is simple primary alcohols undergoes E2 elimination, because I already told you that in E1 elimination we get a carbocation, and for a primary alcohol you will get a primary carbocation. But primary carbocation is not stable because there won't be any hyperconjugation effect and very less inductive effect for it.
Okay.
But if you have a beta branching, as shown in this example, there is a possibility for E1 elimination because you have more inductive effect and there is possible for hydride ion shift, which you will study later on.
Okay.
And For secondary or tertiary alcohols, it proceeds to E1 elimination. Now, one more method for preparation of alkenes is dehalogenation of vicinal dihalides. Now, if two halogens are present on the adjacent carbon atoms, it is called a vicinal halide as shown here. If
there will be a lot of steric repulsion between the halides, right?
There will be. If it is fluorine, there won't be much.
Okay, but as it gets larger, it will be much more. Okay. So, can we pull off the same reaction if fluorine is present there, or we can't?
We can.
We can do it for fluorine as well. Alright. So, it's applicable for fluorine, chlorine, bromine, and iodine.
Yeah.
Alright. But will iodine form such a compound ever?
Actually, it won't exist.
Oh, it won't even exist.
Yeah.
Okay.
But there will be some compound.
Okay. It's a possibility because chemistry always has exceptions.
Yes.
Okay. So let's see how this happens.
When you treat this with zinc dust at high temperature, it will undergo elimination. It loses these two H plus ions and you will get an alkene here.
So it loses both the X ions, you mean?
And zinc gives electrons to it.
Okay. So does it have anything to do with help because we have heat here?
Here there is nothing to do with help because this heat here suggests elimination product, because first you are using zinc.
Okay.
It's a reducing agent because it provides electrons.
Okay.
And after we got electrons here,
alright,
you'll get a negative charge on one carbon.
Okay.
And at high temperature, this gives electrons to this carbon, which favors departure of another halogen ion.
Alright, okay. So now that we are done with the preparation of alkenes as such, let's look at some chemical properties of alkenes.
Yes. First one which you will study in chemical properties of alkenes is catalytic hydrogenation. That is, conversion of an alkene to an alkane. Now, for this use metals like nickel, palladium or platinum in the presence of hydrogen gas. Now what happens is, this hydrogen adsorbs to these metals like this one, and this attacks on this alkene. You will get cis alkene.
So because it's a planar compound as such, it can attack from the top and from the bottom, right?
Yes. But it will give only syn addition because both are attacking from the same side. Either both hydrogens can attack from down or both from the top as such, and the end result will be the same nonetheless. Alright. Now that we are done with catalytic hydrogenation, let's move on to the next part of chemical properties. So we know that alkene is a nucleophile and it undergoes electrophilic addition reactions. The name of the reaction is determined by its RDS, its rate determining step. In the RDS of addition reactions of an alkene, the electrophilic part of the reagent attacks the C double bond. So the first which we are going to study is called the electrophilic addition of HX, where X is any form of halide. We also have a common name for it, for this particular kind of reaction, right? So Gopi, tell us more about it. Here we take an alkene, we treat it with a HX, it's an acid basically. And first what happens is, since it's an acid, it gives H plus X minus, and as I already told you, it's an electrophilic addition. First, the electrophile part of it, which is H plus, attacks this nucleophile, which is C double bond C, and hence you will get this product. The mechanism of it will be taught to you later on. And
also, what is the solvent or the reagent that we are going to use with this?
This is polar protic.
Okay.
Because we are getting X minus here.
Alright.
And
so
here
this is
I've
called
given you that
Markovnikov's addition, right?
Yeah. If you observe here, this halogen X has been attached to the carbon bearing less number of hydrogens. If you see it here, it has one hydrogen, whereas this carbon has two hydrogens. And this halogen has attached to the carbon which has lesser hydrogen. So this rule is called as Markovnikov's rule, which states that negative part of the reagent, or it's also called as addendum,
the molecule to be added. Okay.
Gets attached to the carbon atom bearing lesser number of hydrogen atom.
So that's all we need to remember. But
there will be some exception to it.
Obviously, because this is chemistry. Okay.
You'll come to know it once you look at the solved examples of it.
Okay, so we're gonna have Markovnikov and anti-Markovnikov products.
Yeah.
Okay.
And the very next example will tell you that there will be possibility for anti-Markovnikov's product, which is addition of an alkene with HBr in the presence of a peroxide. This has a very particular name and it's called as Karsh effect. Unlike addition of HX in presence of water or in the presence of any solvent, where you have got an Markovnikov product, here you are getting an anti-Markovnikov product. I'll tell you the mechanism of it later on.
Which means that an anti-Markovnikov product will mean that the halogen will attach to the carbon that has a greater number of hydrogen atoms?
Yes.
Okay.
So now let's move on to the next part of the theory.
Okay. After the last set of chemical properties that we studied, we are now going to move on to the hydration of alkenes, for which we use various reagents. So what are the reagents that we use, Gopi?
Basically we use two reagents for it. First one is dilute H2SO4 and the second one is HgOAc in the presence of water, and then we add NaBH4 in the presence of OH minus. That's a basic medium. Now you can even add alcohol in place of water, and the first one is called as oxymercuration demercuration. If you use alcohol, it's called as alkoxymercuration demercuration. Now,
alright.
For the first one, that's dilute H2SO4, the intermediate we obtain is carbocation, and you also know that for carbocation intermediate, rearrangement is possible.
You mean hydride shift or others?
Hydride shift or even methyl shift if possible.
Okay.
So I've given you an example here. First consider propene. If you add dilute H2SO4, you will get this Markovnikov product. Now consider this example where it's seen that you can see that hydride shift has occurred and you have got neither Markovnikov nor anti-Markovnikov product, because negative part, that is OH minus, has attached neither to the carbon atoms of the double bond.
Okay, so when the carbocation is formed at the second position, it is going to undergo a hydride shift, and there is going to be a positive charge which the OH will attack at position number 3. Right?
This one.
Okay, alright.
Now coming to the next part, that is HgOAc in the presence of OH minus. Now it's very selectively used to get Markovnikov product, and also no rearrangement is possible here. You can see this by the mechanism of it.
Okay.
I've given you an example here where you have used the same compound as we have used in the second example for dilute H2SO4. You will get a direct Markovnikov product. If you use alcohol instead of water, you will get OR here.
Okay.
Now, let's move to the next part, which is hydroboration of alkenes. In the hydroboration of alkenes, we add alcohol to the alkene with the help of B2H6.
B2H6 is that very famous banana bond compound.
Yes,
right?
It is called as diborane. I'll draw out the structure for you. It will be like BBH.
Oh, and this is the 3-center 2-electron bond.
Yes.
Alright. So guys, remember JEE has the tendency to pick up concepts from one part of the syllabus and relate it to the others. As you can see, this is just a catalyst which is used for, or a reagent that is used for a reaction in organic chemistry, but there's a question on inorganic chemistry that can come when they ask you to identify the structure of B2H6 or the hybridization of boron as such.
Yes.
Right? So, well, be very careful.
Now, for this we have got anti-Markovnikov product instead of Markovnikov product. Now you can see this at our solved examples.
Okay, so we're going to deal with this later on in the solved examples?
Yes. Now the next part is addition of halogens to alkenes. In the example shown here, you add non-aqueous condition, that is like FeCl3. If you add water, what happens is
OH will also attach itself?
Yeah, because bromine gets disproportionate to give HBr and HOBr.
Okay.
You have Br plus, OH minus and Br minus.
Alright.
So, in the presence of non-aqueous conditions, you got anti-addition, that is one Br is attacked from above and other Br from below. This is one possibility. And the next one is Br from this below from this to this carbon and above to this carbon. As a result of it, you will get racemic product. Yeah, this is shown here, where this carbon has attacked from this side and one more carbon from above. And for the second case, one carbon has attacked from above to this carbon and below to this carbon. So
you mean one bromine has attacked?
Yeah, sorry, one bromine.
So will we ever have a syn addition in this case, or
no? It will be always anti-addition.
Okay. Alright. And I think there's something that we should be very careful about noting here.
And here the electrophile is X plus, that is Cl plus or bromine plus. Also observe that no carbocation rearrangement is observed here, because the nucleophile attacks and electrophile departs at the same time.
So this is a lot like the elimination reaction as such, right?
This is addition reaction.
So I'm saying as a parallel, this is a lot like E2 elimination or E1 elimination, the one where there is no state produced in the middle.
First it undergoes addition,
okay,
and later it's similar to elimination.
Okay, alright.
Yeah,
but there is no
and departure.
Intermediate transition state that is formed as such.
No.
Okay. And hence rearrangement is not possible.
Yeah.
Also, students, you should be very careful in remembering that we are quite used to having Cl minus and Br minus as compounds as atoms that attack compounds, but here it is specifically Cl plus and Br plus that attack, right?
Now let's move to the next part of the theory.
Alright. So let us start with the last part of our theory for alkenes, where we are going to be studying ozonolysis, which is basically the addition of ozone, the O3 compound. So Gopi, tell us more about it.
The ozonolysis, first for an alkene we add ozone, that's O3, you will get an ozonide. Now it's an unstable one.
What does an ozonide look like?
This is an alkene, let's take. Then the structure of ozonide would be like this one.
Oh boy, this looks very unstable.
Yeah, because for this oxygen, if you take, they have two lone pair of electrons, and this oxygen also has two lone pair of electrons. They repel from each other,
and they're also in the same plane, so there'll be a lot of repulsion. Alright.
And further, there are two types in ozonolysis. One is reductive ozonolysis and one is oxidative ozonolysis. As the name suggests, in reductive ozonolysis, we are reducing agents like zinc, which gives electrons.
Okay.
And in oxidative ozonolysis, we add oxidizing agents like H2O2, H2O plus half O2, or nascent oxygen, which is basically oxidizing agent.
Alright.
Now I'll discuss the mechanism of it in very detail in the examples. Now let's move on to the next part and the final part, which is permanganate oxidation of alkenes. Now in the permanganate oxidation, there are two things. One is in the hot condition and one is in the cold condition.
So what is the difference? Like with the hot and the cold condition, what ends up changing?
Hot conditions provides more energy and it ensures that bond breaks away. So, and KMnO4 is very strong oxidizing agent.
Alright.
And in this very hot condition, what happens is this bond breaks away, and you will get even this H get oxidized to OH, and this C double bond C to C double bond O, and you will get up an acid here. Now for the second case, if you take, similarly you will get C double bond O, and each H gets converted to OH, and two hydrides on same carbon is
very unstable.
Yeah, so it dehydrates and you will get a carbon dioxide.
And carbon dioxide is a very, very stable compound,
yes.
So its formation is favored.
Yes.
Okay.
Now, if you take the cold condition, that's cold alkaline KMnO4. The reagent is very famous one, and it's called as Bayer's reagent. And here you will get cis diols. I'll tell you this. I'll show you this. MnO minus. Basically, this is the structure of KMnO4. It gives syn addition to it.
Okay.
And see, now you can see that it's adding alcohol, oxygen in syn addition, so you will get syn product OH OH.
And what is the use of OH in this medium as such?
Because the OH provide the cleave of this bond. I mean, this will give electrons to it, and this will ensure that this,
thereby allowing cleavage. Oh, so if we had H plus, this cleavage would not have happened,
Yeah.
which is why we need the alkaline condition.
Yes.
All right. So with this, students, we end our section on alkenes and its theory. Let's move on to the solved examples quickly and let's get this started.